So I'm sharing my screen with you. So I have prepared this agenda here. So I think it's nice it's appropriate to have some announcements in the beginning of our seminars. So here we have some conferences I would like to share with you. The first one is this third generation gravitational wave detectors, the view from Latin America, that will be held in São Paulo, here in Brazil, in July. You can have the website
June.
here. Ricardo would like to talk about this conference.
No, it's in June, not in July. It starts on the 28th of June.
Yes, June 29. Okay, June 29 to July 3. Okay. So we have this fourth school of gravitational waves in astrophysics in Chile in January of next year. So I think here is 27. And we also have here this public call of the Ministry of Science and Technology of Brazil for the Latin American Caribbean Cooperation Program in Science, Technology, and Innovation. This could be interesting for our community. I put the website here in the agenda. Also, you could have a look. Okay. So if someone else has other announcements, please, you can just open your microphone and talk. No? If not, so we could start with our seminar. The first speaker is Rafael Mancini. He is a PhD student here at the National Institute of Space Research in Brazil. He will talk to us about the gravitational wave astronomy as a probe for novel tests of general relativity. His advisor is also called Rafael Nunes. Am I right, Rafael? So you can share your screen, and I will just stop to share my screen here.
Okay.
So you can start when you want, please.
So can you hear me and see the screen?
Yes.
So, okay, can I start now?
Yes, you can start, please.
Okay, thank you. So, hi everyone. I'm Rafael Mancini Santos, and my supervisor is Dr. Rafael Aguiar. My co-supervisor is Dr. José Carlos Neves Geral. And today I want to talk a little bit about the works that I've been doing together with my advisors over the course of my PhD. And that's why the presentation is entitled Gravitational Wave Astronomy is a Probe for Novel Tests of General Relativity. So to start, this is a review of the structure of the presentation, starting with a brief introduction. Then I'll talk a little bit about some of the works involving parametric tests of general relativity. And then I'll discuss a little bit the work that I'm currently doing with some people in Italy that I started during my PhD abroad. And then I'll finish with some final remarks. So to begin, the current trend in gravitational wave astrophysics, as you probably are already aware of that, it started in 2015 with the detection by the LIGO collaboration of the merger event GW 150914, which was a merger of a binary system of black holes with masses of approximately 30 solar masses. And over the course of the decade since this first detection, the LIGO collaboration has improved a lot the sensitivity of its detectors, and it got to a point which I think is perfectly exemplified by this latest detection, the GW2501 14, which is a very similar, it's a detection of a signal coming from a very similar system of comparing to the first detection. And I think it exemplifies the effort that was put into improving the detectors, because the source properties of this event is very similar to those of the first detection. They could compare the parameter estimates that were done with these two detections. And what is astounding for me is that the statistical error shrank a lot because of these improvements. So we're getting to a point where we are able to detect gravitational wave signals with a much higher signal to noise ratio, and this enables a lot of novel tests of general relativity to be done, and also poses a lot of challenges because now we need to start to worry about the accuracy of our waveform models and the data analysis pipelines that we use. So as of today, we have over 200 gravitational wave signals detected. And yeah, all this data enables us to do a lot more tests, a lot more science with this regime of very strong gravity and high dynamical field. And to be honest, general relativity has already been thoroughly tested with gravitational waves. There's that recent paper by the LIGO collaboration. It's four papers, 4-part study. They did a lot of GR tests with the fourth gravitational wave transient catalog, and still they did not find significant deviations from general relativity. And someone has to find them eventually, but probably not me. But speaking of that, now I want to talk a little bit about the work that have been done, which is related to the tests of general relativity, in particular parametric tests. And just to give a little brief introduction to parametric tests, usually one starts with a model of a gravitational wave described by some parameters. Some are predicted by general relativity, and other are extra parameters which may come from a modified gravity theory or simply some model that introduce some generic parametric deviations. And what one is interested in is given some data, one wants to compute the distribution, the posterior distribution of these parameters. So one can then estimate like the median of these parameters and all that. And there are some theory agnostic frameworks, which are basically some frameworks that introduce generic parameters, generic deviations to general relativity that facilitate a lot these parametric tests. And one which I want to draw special attention to is the parameterized post-Einsteinian framework, which at least for the spiral phase of the signal is given by this equation on the screen. The alpha and beta parameters just control the amplitude of the deviation, and the A and B control at which post-Newtonian order these parameters enter or starts to become relevant. So the advantage of this framework is how simple it is to incorporate deviations into a particular waveform model. And we use this framework to test two particular models beyond GR. The first one was a beyond care model, And we use data from the third gravitational wave transient catalog. It's released by the LIGO collaboration. And this particular model is the deviation from general relativity is controlled by a single parameter, which is this epsilon 3. It is basically a parametric deviation from the Kerr solution, a classic solution from general relativity. And as I said before, this deviation can be mapped to the PPE framework, and after this mapping, the parameters assume this functional form of these equations on the screen. In this particular case, this metric, the Johansen-Saltus metric, introduces a deviation at the second post-Newtonian order to the phase. And the effect that this deviation has on gravitational waveforms are exemplified by these two plots on the screen. In the left, you can see more clearly the effects that the deviation has on the phase. And on the right, you can see on the amplitude. Although the signals that we use to analyze, they do not have enough signal to noise ratio so as to be able to, so the deviation in the amplitude of the signal comes relevant to the analysis. But anyways, we chose the events, we established a threshold for the signal to noise ratio of 10 to select the events from the GWTC3, and we found no significant deviation from general relativity. But we were able to refine a little bit the bounds on this parameter. The previous bounds were like, it's a modest refinement. But anyway, moving on. The next work I want to talk a little bit about is this one, which we chose a subclass of the Horndeski theory, which is a modified gravity theory. It's called the luminal Horndeski theory because it, as similar to GR, it predicts that the gravitational wave propagates with the same speed as that of the light. And some attention was drawn to this theory because of the multi-messenger detection, the GW17 0817, that landmark detection of a signal coming from a neutron star binary, which we also were able to detect the electromagnetic signals coming from the merger. And people were able to put really tight constraints on the speed of the propagation of gravitational waves back then. So anyway, this particular theory can yield some hairy neutron stars and black hole solutions. In this case, it's a scalar hair. And again, we can map the contributions, the deviations that this theory proposes to gravitational wave to this theory agnostic framework, that is the PPE framework. And the deviations are also similar to the previous work, controlled by a single parameter. There are two here, but they are coupled, so we basically consider them as a single parameter. And this kappa 0 over here, if you set this specific parameter here to some values, you kind of recover some specific theories like the Brans-Dake theory. And this specific deviation enters at -1 post-Newtonian order in the phase. So this plot here shows a little bit how it affects gravitational waveforms. And so we chose 4 neutron star black hole merger events. And the best bound that we found came from the GW 2309, 23, 05, 29, which was this one on the screen over here. And this is just to draw attention to this corner plot, just shows the differences between the parameter estimates as obtained by the LIGO collaboration and the ones obtained by us. You can see clearly here that there are no significant deviations from general relativity. And now I want to talk about another work which deviates a little bit from the parametric tests of GR that I was working on. In this case specifically, the context is dark matter emits neutron stars. It's based on the assumption that dark matter can accumulate neutron stars. And in the specific context that we're working with, dark matter can accumulate in at least two different scenarios. In one scenario, that is one in this left plot over here. These two plots are mass radius relation of neutron stars for this scenario of dark matter accumulating inside. And in this left side here, this is exemplified the situation where dark matter accumulates in the core of neutron stars. So the effect of this F chi here is the fraction of dark matter inside the neutron star. So you can see that when dark matter accumulates in the core of neutron stars, as you increase the fraction of dark matter, the overall equation of state softens a little bit as you increase it. And the opposite happens in this right panel over here, which exemplifies the case when dark matter accumulates as a halo around the neutron star. And in this case, as you increase the fraction of dark matter, the overall equation of state stiffens, as you can see here. And for this work, we chose a particular model of dark matter, which is a self-interacting bosonic model. And one thing I want to return to the last slide because I didn't talk about one very important point. The thing that separates these two regimes is basically the mass of the particle, the dark matter particle that you assume. The case on the left over here is when we consider heavier dark matter particles. And to put a number on this heavier, this plot was generated using a mass of, I think, 400 MeV. And this right scenario over here, the halo scenario, happens when we consider lighter dark matter particles. And in this case, we consider, I think, more or less 100 MeV to generate this plot. So the framework that we used to compute to solve the structure of the neutron star in this scenario of accumulation of dark matter is called the two-fluid TOV equations. It's basically the TOV equations, but you consider both baryonic matter and dark matter as perfect fluids that interact with each other only gravitationally, and you get an equation similar to the TOV equation, but you have another fluid to deal with. They are basically summarized by these two equations on the screen. And as we saw on the mass radius relations, including dark matter and neutron stars, since the presence of dark matter changes the mass and the radius, it will change another parameter which is related to the mass and radius of a neutron star, which is called the tidal deformability parameter. And this parameter quantifies how much the internal structure of a neutron star deforms in the presence of an external gravitational field, which may come from a companion or compact object like a black hole or another neutron star. And this effect on the gravitational waveform is a correction on the phase of a gravitational wave that enters at phi post-Newtonian order. So it's something that really only becomes relevant at the late stage of the spiral phase. And this picture here is a picture that exaggerates a little bit on this effect just to for illustration purposes, but the effect is it's a little bit smaller than that. And since it is so small, we have to adopt a particular strategy to be able to analyze the signals that we have that the LIGO collaboration obtained. But despite that, we were able to find some bounds for the dark matter fraction. And the best bound that we found was this one on the screen over here, which is similar to previous studies. The difference for our study here or our work is that I think we're the first. This work was the first to do an event by event analysis using real gravitational wave data. And now I'll want to discuss a little bit about the thing I'm currently working on together with Dr. Davide Gerosa and Dr. Alexandre Tobiano, both from Italy, Milan. And Davide Gerosa is actually actually was my supervisor during my period abroad. And the idea of this work is basically to try to capture deviations from general relativity in the phase using a non-parametric model. The basic assumption here is that we can write a gravitational wave phase as a contribution from the general relativity prediction plus something that we are calling the phase residual, which can be anything. We want to keep it general. It can be deviation from general relativity, but it can even be differences between waveform systematic differences between different waveform models, like waveform approximates. So this phase residual over here is represented as spline, and I left something here which I didn't want to leave because I was planning to explain a little bit more, but I think I would not have the time to do so. But anyway, please ignore this part of this slide. So these are some preliminary results we did with this model and injection recovery test. The injection was a Taylor F2 model plus a 2pn PPE deviation, and the recovery model was the non-parametric one, well, which was for the GR part of the phase, it's a Taylor F2 model, and for the residual phase, it's a spline. And this dashed black line over here is the injection, and the blue part of the plot over here is the posterior on the residual phase that we got. So, and with this model, we can actually correct possible biases on analysis of gravitational wave data. So this is an example of this running an analysis with using as a recovery model the non-parametric one. And now we are interested in a second phase of this whole design, because a non-parametric model maybe it can absorb some bias, some deviations from GR, but the non-parametric model per se, it does not contain any physical information. So to retrieve physical information from it, you need to establish a parametric model of physical observables. And the second part of this whole pipeline that we are trying to develop is part that has the goal of remapping the non-parametric samples to a parametric model. And here is this is the basic equation of this remapping procedure. This part of the equation is the likelihood of the non-parametric model. And if we run a parameter inference with the non-parametric model, we have samples to compute this part. And this part in the right is the conversion term between the non-parametric model and the parametric model. And this conversion term over here, we define it as a stochastic process. So we think of these samples from the non-parametric inference as coming from a particular stochastic process. And just to give an example, so I already talked a little bit about the non-parametric model, the Taylor F2 plus phi. And the parametric model could be the one that we injected, Taylor F2 plus a 2p-NPP correction, plus a gamma distribution from where we will draw the stochastic samples. We will simulate the stochastic process. And here are some preliminary results. Using the gamma distribution as the distribution for the stochastic process, we recover the parametric deviation here. They recover the remapped residual phase is the orange part here of the plot. This is the posterior of and here is the coordinate plot of the red lines over here. I didn't say that before when I showed that other coordinate plot, but the red lines are the true values of the parameters. So the goals of this work is that future detectors will yield a lot more data. They will be able to observe a lot more in spiral cycles. And with more data, parameter inference becomes much more computationally costly, computational cost. So it will become a little bit harder to do a lot of different parameter inference runs. Sorry?
Sorry, Rafael, for interrupt you. Just to let you know that your time have already finished. So if you could be a little bit more fast, please.
Okay, sorry. I'll try to wrap it up. Okay, so the thing is, bigger data, more computational cost. So with a framework, a pipeline like that, one could do just one parameter estimation. Then if we have an efficient way to remap to a parametric theory, it is easier to test GR against a lot of different alternative theories. And since my time is up, I'll jump these final remarks, which are just generic final remarks, and just say thank you all for this opportunity to present my work to you.
Okay, thank you, Rafael. Thank you so much for your nice presentation. Questions for Rafael. Alexander, please.
One moment.
Alexander?
The next question, please. The next question, please.
Okay.
I have some problem.
Okay. Do you have any other question? I don't see any other hands up.
Hi. Excuse me.
Okay, you can go.
Hi, Rafael. Nice to see you. Nice to see you here in this very important meeting. And nice talk. Very interesting work. I have one question. You can put the slide where you have the gravitational wave profile in the principle, in the no,
the care
is yes. Okay.
Yeah.
You show us this very beautiful profile, but I had one question. You mentioned that you use Potsdamian parametrization or Taylor or something like that. But we know that these parametrizations works well in principle in the merger phase, but in the merger phase or ring down phase, you don't have this parametrization. You have, for example, numerical relativity or Reggie-Wheeler for quasi-normal modes. How do you complete this gravitational wave profile?
Yes. No, but for the analysis, we use only the spiral part of the signal.
In spiral, yeah.
Yeah, because you're right. This parametrization they do not work with the merger of the ring down phase. So that would just bias the analysis. So here was just like to serve as a illustration of the modification, but it's kind of misleading now as I see it, but one should only worry about the spiral part of the signal because these are modifications only to the spiral phase of a coalescing binary.
Thank you. It's why I see in the plot that the extra parameter have effects visible in the profile, but I don't know if this parameter, when you use numerical relativity or quasi-normal modes for the ring down phase, I don't know if this parameter affect this part of the gravitational wave profile. I don't know.
No, this model in particular, it only works for the spiral phase. I don't think people have found a way to make it extended to work with merger and ring down.
Okay, only that. Thanks.
Thank you, Alexander. Do you have any other question? Cynthia?
Yes, thank you, Rafael. I have two questions. The first one is, can you explain a little bit more about how waveforms are processed? I mean, I don't know if, for instance, information about the speed or frequency of gravitational waves should be in the waveforms. Yeah, that's the first question. And the second question is, when calculating the prior distribution, as far as I know, we use the data who came from the interferometers. And then how do we test the general relativity while proposing our own modified models or beyond GR, but using the information of the interferometers, which as far as I know, can detect just, for instance, transverse polarization modes, but not longitudinal ones, or like different velocities of the gravitational waves. And yeah, that was my question.
I'll answer. Thank you for your question. I'll answer the second question first because I didn't get the first one. And then if you could just ask the first one again.
Yeah, for sure. The first question was just about how do you propose your waveforms, or like where the information about speed or frequencies for different gravitational waves are, or where they are, that information. I don't know if I'm explaining correctly,
okay. No,
but yeah.
Okay, I think maybe the thing is, I didn't delve too deep into the functional form of the gravitational waveforms themselves, but all this information would be encoded like here on this part of this psi gr over here. This is the phase, so it will encode information about the frequency evolution, all that about the gravitational waves. And you talked about actually, this is how this is one way of incorporating the deviations into the waveforms. This part here, the GR parts of this equation, these you usually compute using some models that were already developed, because they are very complicated models. People like join together some phenomenological models for the spiral part, some numerical relativity data for the merger part, and then some perturbation theory for the ring down part of the signal. They join all this together to form a single model. And if you like to really incorporate modifications into GR in a really smooth way, you need to incorporate in these models. But this is also a legitimate way of incorporating deviations, and it's a lot easier to do so. And you talked about polarizations and all that. I didn't really.
Rafael, sorry for interrupt you, but we need to start with the Odylio presentation because of the time.
Okay, sorry. Sorry.
Maybe you could discuss in another occasion or by me.
Okay.
Sorry for that.
Okay.
So
sorry.
thank you, Rafael. Thank you very much. So now our next speaker is Professor Odylio de Aguiar. Odylio, you can start sharing your screen, please. I will just make a very quick introduction. Professor Odylio received his degree in electronics engineering from the Institute of Technology of Aeronautics here in Brazil. His master's in space in astrophysics in INPE, and his PhD physics from Louisiana State University. He is currently a senior researcher and professor in the graduate program in astrophysics at INPE. Professor Aguiar has also been part of the LIGO scientific collaboration, contributing to the first direct detections of gravitational waves in 2015 and 2017. He has supervised several PhD students and postdoctoral researchers, helping to build and strengthen the gravitational wave community in Brazil. With hundreds of publications and a very high scientific impact, his work has been fundamental in establishing Brazil in the field of gravitational wave astrophysics. So, Odylio, you can start, please.
Thank you, Marcio. Are you seeing my screen?
Nope.
No. Okay. Why? What about now?
Yes, now we can see your screen.
But when
maybe some problem here. We are not seeing your screen now.
Okay. What about now?
Now it's okay.
Okay. This is a work that we have been done with Julie Edson, myself, Julie Edson, Leandro, Márcio Constâncio, and Murilo Pedroso. A way to cool down to 123K the test masses of an interferometer. After more than 300 observations of gravitational waves, we have this plot shows about 200, but we have already observed 300. we have really started gravitational wave astronomy and also multi-message astronomy involving gravitational waves. The detectors that are doing this are the two LIGOs, the Virgo and the Kagura. The observation plan now is for intermediate run 1 that will start November this year. And the plans for 05 in the future should be established as soon as possible. Now, after 2030, it's likely that 3 of the observatories will step in: Einstein Telescope, Cosmic Explorer, and NEEMO. They will be the first ones to be the so-called third generation. The Einstein Telescope will be underground, 200 to 300 meters underground, and it's a triangle shape with 2 interferometers at each corner, one for low frequencies and the other one for high frequencies. And the triangle has about 10 kilometers side. There is also another shape that is have been discussing for a L shape that maybe they will construct too. We will see. Cosmic Explorer is a project in the United States for L shape, 40-kilometer arms. There is also an idea for a second detector of 20-kilometer arm. The sensitivities for Einstein Telescope and Cosmic Explorer will be much better than for example, advanced LIGO, the white curve, okay? Cosmic Explorer will have 2 phases. The first phase is at room temperature, and the second phase cryogenic. And the Einstein Telescope, the low frequency part of it will be cryogenic. The high frequency is at room temperature. And there is also the NEEMO, Neutron Star Stream Matter Observatory. Now, operating the test masses at low temperatures reduce Brownian noise from the suspensions and coatings of the test masses, increasing the sensitivity of the interferometers. We have already Clios 100 and Kagura already done using Sapphire at 20 K. Now, the future ones will be low-frequency Einstein Telescope using silicon at 17 K and LIGO Voyager at 123 K, and the second phase of Cosmic Explorer and NEEMO, also silicon at 123 K. Now, why 123 K? Brownian noise is also minimized if we operate the test mass at a temperature where it has a 0 coefficient of thermal expansion. This occurs because thermal fluctuations are not converted into amplitude variations of Brownian oscillations. There is no thermoelastic transfer. Now, from some literature doing thermal expansion tests with silicon, they found 2 temperatures where silicon presents 0 thermal expansion, around 123 K, depending which purity of the sample you are using, and about 17 K, okay? Now, so why 123 K and not 17 K to use for those Cosmic Explorer, Voyager, and NEEMO? In the Einstein Telescope project, the temperature of 17 K was chosen from the 2 possibilities. However, this choice makes it difficult to use high laser power in the arms to minimize shot noise at high frequencies. Therefore, this choice led to the interferometer being split into two. One specialized for high frequencies, operating at room temperature, with higher laser power in the interferometer arms to reduce shot noise, and another optimized for low frequencies, which have test masses to reduce quantum radiation pressure noise, and with these masses cooled to 17K to reduce thermoelastic and Brownian noise. In the case of LIGO Voyager and Cosmic Explorer projects, a single interferometer solution was adopted. And to accommodate the higher laser power in the arms of these interferometers, the temperature of 123K, the higher of the two available options, was chosen. Well, how to reach those and maintain those temperatures? At the temperature of 123K can be achieved and maintained by extracting heat through radiation. This temperature is high enough for the radiation transmission process, proportional to T to the square, be effective. But in the case of 17K, radiation alone is not sufficient. Thermal conduction is also necessary. The 17K, the T to the fourth is not high enough. And this is done for the AT project. Now, how to implement this 123K? We can use as an example the case of the LIGO Voyager, in which the plan is to reduce the silica test masses with silicon test masses and cool and maintain them at 123K. This is the drawing of the present advanced LIGO. We have removed some parts here to see clearly the test mass, okay? This is at room temperature, okay? Now, this is the plan for cooling. We are going to use two chambers, two low temperature chambers in blue that you see here, an internal one and an external one. The internal one should be vibration isolation, should have vibration isolation to avoid scattering of lights coming back to the laser beam, okay? Now, the idea is to use those two chambers. The internal one here, you see the internal one only covering these two masses, which is the test mass and the reaction mass, okay? Not including the other two from the quadruple pendulum. Now, we can also include the other two, but what I want to explain is that there is the internal one, vibrate isolated, and the external one. The external one, we are going to run the cooling serpentine. The cooling serpentine will be part of the closed circuit that will run liquid nitrogen in the range of 64K to 76K, in the range that liquid nitrogen is liquid, okay? And there is here the cryocooler cold head, compressor is not shown, that will be the source to cool down, to maintain the liquid cold, okay? Is the cold source. And here is the heat source that will receive the heat from the test mass. And the impellers will keep moving this flux, okay? The impellers will be rotated by magnetic fields. Now, we have done Newtonian noise studies. Newtonian noise is noise caused by variation of the Newtonian force exerted on the test mass. So the impellers you can suppose as being point masses that are rotating, okay? The blades of the impellers you can suppose as mass rotating. So we have done this study, and for the case of LIGO Voyager, for example, if the impellers, the two impellers are at 1 meter only from the test mass, they will produce noise above the sensitivity curve, okay? Now, we have done the studies moving to different distances, those two impellers, and even compare with a sensitivity curve 10 times smaller than the actual design sensitivity curve of LIGO Voyager. And so we found those distances are very safe, okay? We are also done for Cosmic Explorer phase 1, also found these distances, very safe. And also for the Cosmic Explorer phase 2, also similar distance are very safe. At least we need to, for those projects, we need to be at least, if we are using 3 blades, we need to be at minimum distance, I mean, more than this distance. And if we use 5 blades, the noise is smaller. And we also found out that if we use an even number of blades, the noise is even lower. Okay, and we also found that there is a distance, not a distance, a position in the z coordinate. Z coordinate is this one from the center of mass of the test mass. Okay, we found that a special z distance, depending of the number of blades and the distance, depending of x0, we found that there is always a z distance that zeros the Newtonian contribution. This was amazing discovery that we published in this paper. And we also did emissivity studies with silicon, and we found that we predict that LIGO Voyager and Cosmic Explorer will have emissivity, silicon emissivities around 0.67. So they are pretty high. They will remove 7.5 watts if the internal chamber is at 77K for LIGO Voyager, and 15.2 watts if it's for Cosmic Explorer. And if we have a shield lower than 77K, for example, 60K, let's say 64K, we have almost that much of laser power removed. Okay, the laser power removed is the heat deposited by the laser power. We can remove more. And this is a test we have done with water, just to check if we could make an impeller that could move the water, put a flux in the water circuit. Okay, so this is the impeller, was printed using a 3D printer, and this cylinder, hollow cylinder made of aluminum, is for the magnetic field to rotate the impeller. Okay, and this is the thing working with a 3-phase power. You see the impeller rotating and the water flowing. Okay. This is a 3-phase part of the motor. Okay. Conclusion, after these studies, we are ready to do a prototype. So we will develop a closed-loop system of subcooled liquid nitrogen flow driven by impellers between a cryocooler and the cold chambers, containing test mass as the solution for cooling the silicon test mass of LIGO Voyager and Cosmic Explorer, maintaining then a temperature of 123 Kelvin without compromising the design sensitivity. Okay, these cold chambers will absorb heat from the test mass using emissivity of the silicon present in them, okay? With no need of additional black painting. Thank you for your attention.
Thank you, Odylio. Thank you so much for a very nice talk. Questions for Odylio? Yes, Ulloa.
Okay.
Hello.
Hello.
Forgive me. I am new in this area, in this whole area, so I have a pretty basic question.
Uh-huh.
These test masses are fixed or they are allowed to move? I mean, the mirrors in LIGO are fixed or not?
No, they are suspended by wires, and these wires are vibrate isolated from the laboratory, from the site vibrations. So
I
those
see.
mirrors are very motionless pieces. I believe they are the pieces in the planet that move less than any other one.
I see. So the frequency is the same of the gravitational waves detected.
Yes,
I,
they
I
are.
mean, apart from the noise.
Yes, the gravitational waves makes those test masses to move exactly according to the geodetic deviation.
Yes, I understand. And why cryogenic?
To lower the Brownian noise on the crystalline structure of the test mass.
You
So
mean
the mirror
the
will have
temperature of the
less
mirrors?
noise of Brownian motion.
I'm sorry, you mean the temperature of mirrors?
And also the suspension. The temperature of the coating on the mirror, and also
Yes,
the suspensions, the Brownian noise in the suspensions, the wires, will be smaller.
yes, I understand. Thank you very much.
You're welcome.
Thank you, Odylio. Deborah?
Hello, can you hear me?
Yes.
Hi, Odylio, thank you for your presentation. My question is if there is a specific reason for using liquid nitrogen instead of water. Um,
Well, if you want to cool down the mirrors to 123K, you should use a liquid fluid that is liquid at cold enough to bring your shields to very low temperatures, so radiation from a test mass at 123K would be efficient. So the chambers will be around 80K, like I showed to you here. I show here, you see, the chambers will be at 80K or even lower than that. Okay, 64 if possible, 64, 60, 70K. So to remove as much as possible heat from the test mass. The radiation is proportional to T square of the source, the heat source, and the T square of the shield source, the cold shield. So if the cold shield is very low temperature, T square will be very small, and 123K to the fourth will be high enough, so radiation process is efficient.
okay, thank you so much.
You're welcome.
Do we have any other questions? If not, I would like to thank you, Odylio, so much for your presentation, and thank you, Rafael, for your presentation too. I just would like to share my screen for a moment, just to show to you I have included 2 other announcements that Alexander asked me to include in our today agenda. One of them is about the open data workshop that will be held next week, and also have this other event that is the North American Einstein Toolkit workshop and school. You have the links here in agenda. I have posted the agenda in the chat. And also our next seminar will be in May 40th, but we do not yet have speakers for this date. So I would like to invite anyone who would like to present a talk to the Latin America community. We have this spreadsheet here. I have also posted the spreadsheet in the chat, where you could just include your name, and then we will contact you to make the announcement of the seminar. So, Claudia would like to say something. Enea?
No, by my side. Thank you.
Okay. So, thank you all.
I think
Yes?
Sergio may give a talk next month, but he will confirm you later. Thank you.
Okay. Nice, very nice. Thank you, Enea.
Thank you.
Thank you so much. Okay, so thank you everybody for attending our seminar, and see you next month.
Thank you all. Bye.
Bye-bye.
Thank you.
Bye-bye.
Thank you.
Thank you.
Thanks very
Bye-bye.
much. Bye-bye.